in C++ 17, this is how you will do hello world. Well, this cout and hello world will stay. But what you would say auto, of course, hello. Sorry, const char star s. No, I'm old-fashioned in this way. How about p? P better, because I'm going to do this. While it's not null, I will yield star p plus plus, and here I would say for auto. Okay, good. C, I'll call hello. I will pass it hello world. I'll pass it hello world. Okay, and now C. Formatting is not good, so let's fix the formatting. Let's see. Okay, good. So we're good with format. Run it, and look at that, hello world, 17 style. Good. And what happens here is when we do yield, you will see the stack, right? There's a main. It's called hello with some funny prefix. We can strip it out later, but it doesn't really matter. Then we yield, oops, we go back to main, and then we pull again, and we back to hello. So that's coroutines. Okay, done. No, it's an old thing, and actually, coroutines used to be way better than they are today. So imagine that you are in the year 1958. So you take your favorite COBOL program, and this is not a collusion. John Culp, who had a punch cards and the COBOL program in his previous slide deck, and me, it was completely independent. So, and then you pass it to the most modern 9-path COBOL compiler. And this is from the paper in 1963 by Conway. And this is the first time coroutines were mentioned ever. So how this guy would try to deal with your program. So what it will do, it will start the main routine that will go to the basic symbol reducer, which will eat the punch cards and then spew the tokens onto the tape. And then it goes back to this main routine. And main routine will now call name reducer, which is like name lookup for us now, but a whole path for that, which will read the tape and then put the result out on the next tape. And they will keep going. And eventually you will get the thing you wanted, the result of the compilation, and a whole bunch of extra tapes you no longer need. There was this guy who thought that it is absolutely insane that to pass a token from a lexer to a parser, it requires this whole expensive piece of machinery, okay, just to pass a single token. So he thought that functions are just like, it's not good enough. We just need to raise a level of abstraction a little bit. Subroutine is just a little subset of a more general abstraction, which is a coroutine, which allows you to write the code the same way, but pass the stuff directly. So, and this was another guy who at the same time invented that concept, but he never published a paper, so his name is forgotten. So if we think about what functions are, they support two operations in the way how they relate to other functions. So S stands for suspend, and the first circle is what happens to me, to this function. And the green circle, or the right circle, the second circle, is what happens to another function. So the first operation that function can do with respect to other functions is suspend itself and activate a different function. Now, when you're suspended, all of your local variables are preserved, including exactly the spot where you are. And the second operation that functions have that do stuff to other functions in relation to other functions are to terminate itself, to destroy all of its local state and yield back to the caller. And you probably all know the other names for those fancy circles I've drawn, right? So what is the first operation? Yes, it's a function call, yes. And the second operation is return. It's either return statement or you hit the curly at the end. That's what functions do. And coroutines can do all of that stuff because coroutines are more generalized functions. They have the call and return. And let's mix up the circles a little bit. They have this funny thing where you can suspend yourself, but instead of doing a function call and activating a new function, you actually yield control back to whomever called you. And this magical third primitive is what allowed Conway to make 9-pass compiler, which used big, expensive, slow machines to pass a token from a lexer to a parser, make it into a function call. And that's how essentially it went. So the main called the basic name reducer. This guy tries to call read token. It used to go to the punch card write routine. But instead, the little helper read token would say, oh, I can talk to a coroutine. I will activate that coroutine. It will start going, and at the point where that coroutine will say output token, I will suspend it without killing its state, without terminating it. And I will yield back to whomever called me. And that is exactly what we saw at the very beginning with hello world, because the hello was yielding back to the main and then jumping back and forth. So with this new, improved, generalized routines, he was able to do what nobody believed was possible. Nobody believed it is possible to write a one-pass COBOL compiler by humans. They thought that they may invent compilers of compilers where they will try to like munch the code, wonderful state machine, but it's like nobody believed you could write it. And with coroutines, yes, we were able to compile your entire COBOL program at a speed of 100 cards per minute. Unbelievable. Now, this is an example, maybe, of a negative overhead abstraction. Essentially, it's an abstraction. When you raise the level of abstraction, suddenly your stuff is not only simpler, shorter, neater, tighter than before, but also much faster. This has been forgotten about coroutines. Since those times, since those old times, people try to imitate that by inventing cheaper versions of the tape machines. People try to imitate coroutines using threads, using fibers. But they have forgotten that coroutine is just a generalized function. It should be as fast as a function and faster. Okay, we no longer, at least most of us here, do not write COBOL compilers. So maybe this problem is not so relevant to us. So cover your eyes, we're going to the future. Okay. I was just warned that transition from dark to white will hurt the eyes, so I made this little, anyway, thank you, Andrew. Okay, so remember the diagram of 9-pass compiler that we had before? Actually, we cannot solve much simpler problem. Look at the state machine. A problem with problem description that's simple, it must be simple to write, but it is not. Of course, if it's synchronous, yeah, we can write it simply and straightforward enough. We'll say, well, yes, this is how many bytes you want to read. Yes, I need some buffer. I will initiate a connection, and when connection is done, I will start a loop. I will start reading into a buffer. It will tell me how many bytes it read. I will have some terminating condition. You know, if it's no, if a number of bytes read is 0, connection is gracefully closed on the other side, so I have to bail out. Or if I've read enough, I bail out too, and I will tell how much. Okay, it's simple. So how do we write it asynchronously in C++ today? So there are two ways, and I will show you two possible ways how we can do it in C++ today. in C++11, there was this pair of types introduced, promise and the future. And this is essentially a channel which allows you to transmit a single value from one party to another. It is a rather heavyweight mechanism. You can see to implement that we have intrusive pointer pointed to the heap allocated shared state, which has atomic ref count, and a mutex to guard the state, and a variant which can contain value is not here yet, empty, or here is value of t, which is the end result of it. And if an operation wasn't able to produce that value, it will be an exception pointer. And we need a conditional variable so that the guy in the future can block. And notice, this is not helpful for asynchronous programming. This is fine for fork join, where we launch a bunch of operations and then we block, waiting for them to complete. So to address that, in C++17, we will have .then, and probably some of you have seen Arthur's talk yesterday about concurrency TS. So let's see how it goes. What concurrency TS did, it added an ability to provide a continuation. Essentially, you supply to .then a function object, and you tell the future, hey, future, when you get the value, like call this function object. So now we call TCP reader. Remember, the functions, they have this funny little operation in the end. When you return, you must kill yourself. There is no way to return back to the caller, yield back to the caller, preserving the state. Therefore, whatever we used to have in the synchronous function must go on the heap. So here I have a struct with all of the variables I used to have before in the synchronous version. I stuff them in a struct, I put them into the heap. Now I will do TCP connect, and because it's asynchronous, and in this case, let's say it returns a future with .then, I will say .then, after connection is completed, it will actually give me a future, which is already ready to go. It has either exception or a connection itself. Then I will grab that connection from the future and push it into the state. And now I need to do a loop. .then doesn't do loops gracefully, but it's easy to make this little helper. That essentially, you can see, I will give it a function of future that returns future of bool and takes no arguments. Essentially, it says, hey, call this guy in a synchronous fashion until he says, please call me. And now we can write a body. We'll say body.then, and then when the body completes, it continues with this lambda, and it will tell me done or not done. If not done, then I will go and recurse in some way back into myself. Otherwise, I will return a future which is already ready. This is a very helpful function which allows you to make a future which is ready. If it takes an argument, it deduced what kind of future it is. If you give it no arguments, it's a future of void. So let's continue. Now we can use this helper. So return do while, and we give it a lambda which returns future of bool, and then we will check, do we need to read at all? Nope. If not, we'll say make ready future false, initiate connection, then we will get the bytes thread, and if nothing, so yeah, we're done. Now, who wants to write code like that? Or who feels comfortable to write code like that? Excellent. Oh, there was one hand. So, James, this code has a bug. Can you fix it? I will tell you where the bug is. So the bug is very, very simple. See, I forgot the return statement. Because this function before, I wanted to return back to the guy who called me eventual return, not immediate, but eventual. Number of like, what is the remainder? Did I read everything you wanted, more or less? So I forgot to include that in the program before. So the only thing you need to do, James, this is not orchestrated, he just raised the hand. I didn't mean to pick on him. Is you need to return the total. And by the way, James is the guy who does the very important stuff for the C++ library team. So he's an expert. So James, How do I fix it? Okay, let's go easier. The fix is either on this line, or on this line, or on this line. So just tell me which first, second, or third. Okay. Enough torturing James. So the fix is here, because I need to connect .then to, I think, somewhere here, to this do y, I think, or maybe here, I mean, the point is, it is unreadable, unwritable, unmaintainable. So never, ever write this code. But what do you do? What do we do today when we want to write this code? Actually, the technique is, there is a very, very, very good technique. It's called callbacks. Don't forget about callbacks. They are good. And this is the way how state machines have been written for, not centuries, but tens and tens and tens of years. If you have a state machine, do it as a state machine. Okay, put a state there. Then for every arrow, write a member function. And they will be rather small. For example, the start is just allocate the reader, connect the future, start the connection, pass the lambda. And you see, lambda, to make callback model good, lambdas should be small. You just forward to the thing which actually does and also has a name. OnConnect is a good name for that thing. So now 2 questions. Why do I have p-release here? So what would happen if I remove the p-release? Yeah, absolutely. So correct answer. In this case, I do not like, making extra interlock increments, decrements, atomic operation. I want to have this thing to be just plain unique pointer, and the ownership of this memory will be in the asynchronous activity. So if I successfully launch that and it didn't throw any exceptions, then it owns it. So I transfer the ownership inside. But if there are any problems, then this exception will be thrown and we will never get to p-release. But if we get here, then all good. And this is the same reason why I had to grab the future from the promise before. Because by the time I'm here, it could be too late. It could be gone. Now, OnConnect is very straightforward. We're checking an error code, we transition to the error state, and we grab the connection. So, that's all very similar. And I think if what you have are plain functions, this is probably a better way of writing asynchronous code. And in fact, if you look at Boost ASIO, that's essentially the model it most efficiently encourages. So all of the functions there, asynchronous ones, they have the signature. You have a bunch of parameters to pass, and eventually it takes a function object at the end, which is the completion. Okay, so we have written and crafted state machine, and I completely biased you because I thought I would ask you which one would you prefer, but this is it's an easy answer, this one. Okay, but still, we're not here, we're not there in terms of making it, well, it is close, but can we make it even simpler? Because the synchronous version was pretty much trivial. So what coroutines do for us, they add us this wonderful operation which called suspend and yield, not called that, but mentally in the circles model. I suspend myself here, and await keyword marks that point, and yield control back to the guy who called me. But because I haven't finished, I did not provide the result to him yet. I cannot, because I don't know it. Result is right here. It's in the future. I will return a type that can represent that concept. It doesn't have to be a future, but that's the vocabulary term we have right now, so I use the future. So that's pretty simple. That's awesome. And you also have seen this in other languages, so that may be not the most surprising thing. But what do we pay to get that? Yes, Richard will suffer. Richard is the maintainer of Clang and some other compiler vendor, but not counting compiler vendors. What is the cost? Let's measure. So that laptop, I just compiled with the RTM version of Visual Studio. I'm just trying to transmit 1 gigabyte over a loopback IP. And both sides, the server and the client, are written in the same fashion. So either callback fashion or the coroutine fashion. So let's see the numbers. Okay, first row. One of them is just horrible, it's 0. Another one is okay, it's 380. Another one is 30% better. Good. Let's look at the object size. On purpose, I haven't used any extra libraries because they bring too much stuff. So it was just a little abstraction over raw OS for both callback model and for coroutine model. Okay, what is this? It's Hello World. Just to get the baseline. And yeah, I know it's embarrassing, Hello World 9K. I didn't have time to figure out how we can compress it, but just to give the baseline, do nothing, it's 9K. Here is handcrafted, and here are coroutines. So with coroutines, not only your code looks better, not only your code runs faster, it is also smaller. So these are the coroutines which were meant to be 60 years ago. Because back then, coroutine was just an idea. They were doing it in assembly. Now we're given a syntax, a customization ability that allows you to achieve these characteristics of being a negative overhead abstraction. But you don't have to go to assembly to get it. Okay, why? Like, what is the secret? Easy. You see, with traditional functions, even the best state-of-the-art library like Boost AS.io, you are still too far from the metal. Coroutines bring you closer. And we will just see that. We will see exactly the abstractions that I have to build up to consume raw OS. So what do we have? This is what the user writes in the traditional model, right? I pass a lambda as the callback parameter. Then this is the signature of a function that takes, whatever, and we'll call it later. But this is what OS expects. Overlapped on Windows, unpronounceable thing on POSIX, whatever. But it's the same idea and spirit, that there is an asynchronous separation, and you need to give it some kind of context. It will twiddle with it. And it has to stay stable in memory for entire duration of the asynchronous separation. So what good libraries do, they would combine a heap allocation of a context that have to stay stable in memory. It cannot be a local variable, with the function object. So it's just one allocation. And let's write this. So we want to do this. We want to take OS context that I have to have, and I want to glue to it a function object that user wants to call whenever the operation completes. Sorry, use virtual functions. You can probably do longer, but without virtuals, but I will just use virtuals. So essentially, whenever OS calls me back with a completion packet, I will reconstitute myself back into unique pointer so that whatever happens, I will delete that heap allocated thingy. And then I will invoke an abstract function here. And then I provide, okay, I'll explain that in a second. Then I'll provide the real thing, which will combine your function object with the overlap based. And I override the invoke to actually call the thing you want to be called in your function object. And a little helper down below, just a ramp function that will create the class and allocate on the heap. So one thing you need to tell to the OS or a thread pool or whatever is that whenever an asynchronous operation completes on this handle, call this callback. So that's how the linkage happens. Sometimes OS API says, hey, here is the callback to call, give me a callback and I will call you back. Sometimes it's like hey, just tell me for this handle what callback to call. Whatever happens, it will be called using that callback. Okay, good. Now let's finish it. Using this helper, let's finish the read. This is what user writes. This is what the API looks like, but now we can see inside. So inside what it's doing a type erasure. It erases the function object that was passed from the outside, and then passes to the real read. Again, the only thing that real read is doing, it just strips out the unique pointer and calls, say, OS API. This is just like platform abstraction layer. It has nothing interesting inside. Then I check an error. If there was an error, there are two kinds. The error could be, I don't have a value for you. I don't know what actually, just, there is no value yet. It's pending. And that's okay, because later OS will complete me. Or it's a real error, I will invoke the callback. And in either case, if everything is great, I will release the ownership of the unique pointer, because now the asynchronous operation owns this this little structure with the function object that we created. Okay, good. What happens here? What do we have to write to make this possible? And why it is efficient, more efficient than what we saw before? Just 2 slides, it's not big. Okay. So what do you await upon? So you await upon any type that satisfies a waitable concept. And conceptually, it's conceptual future. It's not real future. And what is conceptual future of T? So this arrow is a timeline. It's a time. And this T is the value T. And this arrow pointed down, it's the present. So essentially, there are 2 possibilities. The value could already be with us, something happened in the past, or it could be in the future. So we need some way to ask about it. So awaitable has to provide an ability to ask that question, and await ready does exactly that. Give it an awaitable, it will tell you whether it's ready or not. Well, if it's not ready, then compiler will form this function object called coroutine handle and give it to you and says, hey, please call me back whenever you know that the value is there. So that's what the await suspend does. And eventually, operation is done. Now I want to get what I want. Say in case of the async read, I want to get, here is the number of bytes you've read, or maybe an exception, or whatever else the operation wants to return to me. So await resume is that part. So when we resume, it allows you to unpack the awaitable and give you the thing you are looking for. So let me show you a little pseudocode of what compiler is doing. Essentially, it's the same thing on the previous slide, just with code, whatever you like better. So we check whether you are ready, and if you are ready, we'll just jump back to the end and resume you with whatever this function returns. Otherwise, we'll suspend you, and this is the magic line. This is the magic line where compiler just suspends this coroutine and yields back to the guy, to whoever called it, without killing any state. Okay, remember this. This was our base class. It's the way how we can link the OS context that OS wants with the code that we want. So with coroutines, it will look very, very similar. So yeah, we inherit from async context. So what is different? There is no virtual functions, but maybe they're inside of this coroutine handle. Well, not really. It's a void star on purpose, and no destructor, no ref counting. It's just a void star with the fancy template, syntactic sugar on it. And we don't want to do PL1, where a function, or at least how I remember it, used to be able to have multiple entry points with different parameters. No, you're not getting that. You get the initial entry point where you pass all of the parameters you want. On resume, you pass no parameters whatsoever. So this is essentially how you pass parameters inside, how you transfer it. You have a, here I stored error and number of bytes. And when OS calls me, I will grab the overlap that OS give me back. I will reconstitute myself. downcasting. Then I extract an error from the completion packet, and then the bytes transferred here. And depending on your APIs, actually this copy is not necessary, because you can actually make your inner loop, whatever in the thread pool stuff out, just pass an address of an error and bytes transferred. Then it will directly go there as opposed to this intermediary completion packet. But in any case, this is the base part. Now let's see the rest. Oh yeah, I'm just breaking that. Resume is also very, very cheap. And we're experimenting with different kind of code gens. And yes, control flow guard will add extra checks, but in the simplest, most efficient, and hackable form, this is how it will look, or might look. What else? Let's finish it. So just as a reminder, I keep the previous slide here, and now I want to write an async read. And the only thing it does, it creates a local class, awaiter, and immediately returns it. So now we need, in that awaiter, we need to define three things: await ready, await suspend, and await resume. Well, it needs some state, right? I passed this buffer and length. I need to capture. So essentially, the operation is not launched yet. I just defer the launching of the operation. And I am not ready. I haven't launched an operation. Moreover, I want compiler give me the coroutine handle to be able to to resume the coroutine. So in await suspend, I will take this handle that can resume the coroutine and stick it into the resume field in the awaitable base, so that whenever OS resumes, it can call it and we are good. I will call receive. If receive give me an error, which is not IO pending, then I throw. Otherwise, I'm good. And when I resume, I will check whether I have an error, I will throw, and then I return bytes. So this is all the code you have to write to do this. There is no heap allocations. This is all inlineable within reason. So this is pretty much as fast as it can go. But I feel bad for the traditional case. Can we make something better? Can we improve the other side? Well, let's see. I profiled. Nothing in the profile really sticks out. Shape is the same. Yes, this guy below doing allocations, but they're not very large part of this execution. So what else can we look at? Well, I checked that 50% of I/O has completed synchronously, and 50 was asynchronous. And by default on Windows, whether I/O completes synchronously or asynchronously, a completion will be always posted to the thread pool. Now, this is actually a very good default, because for server applications, it works out okay. But in this particular case, changes this default behavior by changing the mode of notification would actually be good. So if I set this flag, it means that if a sync operation returns success, it will not attempt to post a completion. So let's modify our infrastructure layer for the traditional model to support this optimization. So can we do it in abstraction layer? Let's try. If I set this flag, it means that if socket received give me success, nobody ever will complete the function. So one way to do it would be just remove that. So I will call invoke either on error or on synchronous completion. And otherwise, I will just release the unique pointer and let it fly. Anybody see a problem with that? Richard, don't answer. This is the problem. You see, we could be unlucky. We could get a string of synchronous completions, and we're trying to push like gigabytes and gigabytes of data. And if string of asynchronous completions is long enough and we're unsuccessful, we can get a Stack Overflow. Yeah, but tail call optimization, sure, maybe sometimes in O2 it will not crash. But in a debug, you might. Not good, not good. We actually, for this particular case, need to implement it on the user side. Again, with sophisticated thread pools, you can give hints. If you look at current executor proposals, there are modes where you can say, post, which is definitely post, or maybe defer. In this case, we could have deferred this invoke. It's one way, but I don't have, any thread pool support. I'm just showing you what to do in a raw code if you have no libraries, no nothing, no anything. So I would modify the read to give me a bool which says synchronous completion or not, and then I will just do a little do-while loop. Okay? Okay. Let's see what happens. Excellent. We are getting close to coroutines. Good. But to be fair, let's do the same optimizations to coroutines. So here, I need to touch this function to make it work. Essentially, I need to be able to veto suspend. I need to be able to say, look, I know I meant to suspend, but I just discovered there is no need to suspend. And we support that. If you change the return value of await suspend from void to bool, and I don't feel good about this strange behavior, but at the moment this is how it works. Then the compiler will check, did you actually mean to suspend? And if you say, oh no, never mind, it will just go back to resume. So this is all I had to do to enable that optimization. Notice that user code didn't change at all. I just tweaked the bottom layer, the abstraction layer. And this shows how the expansion changes. We go from here to here. So it's very, very similar. Let's measure. Aha! And this is the motivation. This is why I will do the Yaki await ready, but twice as fast? That's good enough motivation. So I still feel bad about the handcrafted state machine. Can we do better? Let's profile. So who can notice something interesting that appeared now? Anyone? Well, actually, last time we were discussing that, I think Bjarne asked, but why don't I see allocations? Yes, you are saying there are so many more allocations which are going on. Well, luckily, this is the case. Notice, now the biggest costs are allocations. Finally, we were able to reduce the overhead of whatever OS is doing low enough, so now we can see allocations. Good libraries like Boost ASIO, they have wonderful, wonderful allocator to lessen that impact. It's a thread caching. It's trying to reuse your things. It goes to reuse those little overlap thingies. So it's good, but it's code to run. Where with Coroutine, there is no code to run whatsoever. And let's see if we can fix allocations. Can we get to Coroutine level of performance? So again, you can go the hard way. You can define very, very sophisticated allocator to lessen the impact. But in this particular case, we keep passing the same lambda to read in a tight loop. What if we simply don't call the upper layer? What if we manually call our type erasure, get a handler that we need to pass to the bottom API, and pass it directly? Again, it's an error-prone, it's hard, but we can do it for the type loop in some application after we profiled. So the code will look not horribly, just need to make sure that nobody, this is it. Do we get to coroutine performance? No, we don't. We still run more code. Oh, sorry, but it was a good change. Notice the size also went down. Again, not to the coroutine level, but still good. So, no wonder coroutines are popular, right? Nearly the same syntax in at least 4 other languages before us. But what is different? What is different in C++ from any others? I'll have 2 slides. One is philosophical, another is practical. So philosophical slide, we actually, if you look, actually no, I'll slow down. So it's a generalized function. We're just raising what function is. And when a user gives us some code, compiler will look at that code, and I use some random dragon so that nobody's offended. And if you happen to use await, it will be like a task. If you, okay, one more thing. So future, right? Future has 3 possibilities. It has no value yet. Here is the value, and here's an error. There is another class which is similar, but it has 1 less of a value. That is value or expected of t, where there is no temporal aspect. Well, you know what? You can apply to that too. So it can help with expansion. So it's await and no suspension. Keep going. If you use yield, it's a generator. If you use yield and await, it's an asynchronous generator. And if you use none, it's POF. Who knows what POF stands for? Yes, played on function. Good. And I expect a question. Are you making compiler a language that complicated? Does C++ have to care about all of those things like other languages do? No! Compiler doesn't care. Because who cares is Coroutine designer? Because compiler just giving you this generalized function abstraction, but semantics is trait-driven. Depending on what Coroutine designer, which is you, it's not hidden in the library, defines, you can get all of those and maybe more. We don't know. We release the language change, or will release, and then we will see what happens, what kind of crazy abstractions you can invent with that machinery. So this is philosophical. This is how we are different from others. We are trying to stay true to the original, 60 years ago, where coroutine is a generalized function. We're not trying to make little, well, not hacks, but okay, ignore that. Practical considerations. So these were design principles that we used to, focus our design, to give us answers where to go. And that answers, we want scale. We want coroutines to be scalable to billions. Like, in a browser, you can make every character a coroutine, maybe, or maybe a picture. Just, don't worry about that. You can have as many of them as you want. And also, it's a function generalization. That third operation, suspend and yield back, should be as fast as the call. So you should not be concerned about that. It should be as fast as the function call overhead. Another one, we wanted coroutines to be integrated gracefully with the rest of the world on 2 sides. From the outside, coroutine is a function. It's indistinguishable. You can put external C on it. You can put it on the ABI. You can store it, in a std function, void pointer, void function pointer, function pointer, right? Then you saw the other side. When you are trying to communicate with some other library or OS, coroutine is just void star for them. You pass that void star context, and then we can reconstitute back in a callback and resume the coroutine. So we interact without overhead on both sides, whoever calls us directly or indirectly. And the previous slide explained that point, is that unlike other languages which define that, okay, if it's a generator, it's that class. If it's a task, it's that class. We don't want to do that. We want to use coroutines for whatever you can invent. So they're open. And finally, we wanted coroutines to be usable everywhere. Even though my example before was showing exceptions, you can actually use coroutines in environments where you cannot use exceptions, like kernel node drivers. They need help, so this is the help. There should be no reason for you not to use coroutines when you have them in the language. And there is a proposal going through the C++ standardization committee. There is an experimental version in RTM Visual Studio 2015. Clang implementation is in progress. And this was presentation narrowly focused on one aspect of coroutines. If you want to see more of an overview, you can look at last year's presentation. Latest wording is in this paper, and expect fun stuff in Kona in those papers. And thank you. And there were a lot of people that were doing work, contributed in various different ways and not mentioned, and people trying them out. It was actually quite very helpful. Some of the design changes between now and between previous meeting and this one are driven by customers saying, oh my God, you just broke what you had before. So we fixed some of those things. And do you have any questions? Yes?
What happened to the co-await and co-yield?
Okay, the question is, what happened to co-await and co-yield? So if you look at the wording paper, it has the keyword placeholders. There was no official vote on the matter of what exact keywords we're going to use. There was one definite vote. There were two votes with respect to coroutines at the next meeting. One was, we shall not have a tag on a coroutine like other languages do. So notice, we didn't have any marker on the coroutine itself. And second vote we had was, you absolutely cannot take yield as the real keyword because it'll destroy the world. So there are some papers which are trying to address that. So the keyword question, wait for it. We haven't finished that part. But conceptually, that's how they will look. We need to solve some lexical issues. Yes, please.
I have a question. I was wondering, could you tell us how does it compare to boost coroutine and possibly related? Could you explain the difference between the stateful coroutines and stateless?
Sure. The question is how this relates to stateful coroutines and stateless coroutines. Okay, I'm looking for a nice way of saying it. Okay, the theme of that presentation was, you probably got this, is that we are the only coroutines. The rest are imitations, because none of them are true to the, wait, show me the slides. No, this one. Sorry. So only our coroutines are generalization of a function. Not yet? What's going on? Await, thank you. Excellent. Excellent. So coroutine, we treat them as a generalization of a function. Now, I talked about dark years, dark ages, between the 1960s and now. What people did, they tried to imitate coroutines. What people were trying to do is, hold on. What people were trying to do, they were trying to make this thing cheaper. They did not do that. So boost context is the thing which powers the boost coroutine. And it's magnificent, it's wonderful, it's great, it's cross-platform fibers. You know, in Windows, we only have on Windows, right? And Oliver Kowalski did that for all of the platforms. So they're great, but they are lighter weight threads. And your programming style is, if you do threads, you can make, your programming with fibers, cheapens the cost of context switching, you can make your own fiber mutuses. So it is a valid programming style, but if you are trying to build a coroutine out of heavyweight things, the coroutine you get will be heavyweight. So in that sense, fibers are great. They're useful in certain scenarios. Use them, but that's not this one. So this is, I think that maybe it would be useful to have a fiber in the language, in the standard library, but it will not be a coroutine by this definition. It's not a generalized function. The question is, why would you use fibers? So one example I heard was, imagine you have an application like the one that you mostly cannot change, you cannot change, right? And you want to remove this expensive thing without changing this code at all. So what you would do, you will create a library, helper that will allow you to do the context switch between fibers, and thus lessening the impact of that. Because coroutines require, as proposed today, require syntactic marker. There are some ideas how in some cases we can avoid it, but they haven't been completely explored. But maybe for some scenarios we can avoid the syntactic marker of the suspension point. But in general, fibers allows you to just do that directly without altering any code apart from the inside. Whereas, right, so definitely coroutines are intrusive to the code base, but again, implementation-wise, if you return futures and used to do futures in the rather convoluted way, now you can do it in a simpler way. Yes? So we use operator new to allocate it by default. But in some cases, compiler can elide it when it knows that lifetime of the coroutine will not escape the lifetime of its caller. And I was talking about those traits that guide the compiler transformation. Well, you can you can overload operator new there, and that's how you can put your own allocator. But yes, because we have to suspend using the current existing calling conventions, the state that has to persist across resumption cannot be stored on the stack unless, in a very special scenario. Yes, please.
Will you be able to use these coroutines with standard algorithms? Do you have to write a special coroutine here?
Well, I think I have an example of using a coroutine with a standard algorithm. But essentially, if somebody implemented a generator that returns a sequence of values, the generator itself is iterable. So you can say .begin, you can say .end, and pass it to any algorithm. So now you hooked up generator to an STL algorithm. Let me show you. Let's see, I'm not sure I will show you a demo of it, but I have it somewhere, I just don't want to look for it. But let's see, do I have it here somewhere? Oh, good, you don't see what I'm doing. Excellent. Almost there, almost there. No, here. So this is an example of, let's skip that. This is a recursive generator. And I'm trying to solve the problem, same fringe, where you are trying to traverse two trees, and you want to check whether traversal of those three in order, depth, first, like there is a bunch of words you have to use before that, results in the same sequence of values. So here's what we're doing. We're saying flatten the tree 1, flatten the tree 2, and they both return to generators hooked up to a coroutine, and then you say equal. And with ranges, you would even be able to avoid this entire template. You just say equal, flatten 1, and flatten 2. And what happens is that those guys, at this point, nothing has run yet. Coroutine is created, but no values are produced. So it's only when equal will start saying to the iterator, plus plus, or dereference it. That's where it will activate the coroutine and we'll start getting the values. So yes, you can interact with that. over in the corner. Oh, yes, yes, please.
How does that just compare to new context in Cursive?
Can you tell me more about your concepts?
I think it was deprecated. Like,
Sorry, but is it a fiber-like thing?
no, I don't think so. I think it's,
Yeah, I don't know, but essentially, you cannot imitate these coroutines without a language support. So whatever you can do with OS primitives or with library primitives, you cannot get to this level of efficiency. Yes, please. Okay, so the question is that there is a work, C star something, which looks into improving features, making them lighter weight, and having the runtime to make certain guarantees that we can avoid locking. And the question is, well, how those things are related. So remember the slide, which I will show again because I really like it, where I said that compiler does not care. What synchronizations you are talking about? Like in the standardized warning, there is not a single line saying this synchronizes with that. Because coroutines don't have to be used in a synchronous fashion at all. You can imitate coroutines with that. Running everything maybe on a single thread, just using a queue scheduler or something like that. So this is fully in the hands of a library developer. Like just for fun, I did a little experiment how a future would look like if we had coroutines in the language from the beginning. It's a pointer and no synchronization whatsoever and no heap allocations too. So, but it doesn't handle cancellation. I think the real future should handle cancellation, but that's for the future. So I think it would be interesting for developers of C star library to play with Microsoft or Clang implementation and see whether we have sufficient, customization points that can make the C star futures at least as fast as they are today, but I'm pretty sure they will be faster than you can achieve because you can combine the promise part with the coroutine itself. Oh, session is over. Thank you very much, but I'll hang out.